Hey, hello everyone. I hope you are doing great. So with this video, we are starting an initiative taken by Open Source Study, through which we bring to you all the research done by the student in universities all around the world. This will not only help you to understand or choose your research topics, but this will also help the hardworking students who are putting their efforts and time by giving them a platform to share their interesting and amazing research work. So enjoy the video and don't forget to subscribe to the Open Source Study channel because this is just the beginning.
My name is Gopan and I did my MSc at Delft University of Technology. So I followed the MSc program in Sustainable Energy Technology, which is a very interesting program where you focus on the design of renewable energy systems. So in my case, what I did was I specialized in offshore wind farms, and for my final year master thesis, which took 9 months, I studied how to model the installation of offshore wind farms in the North Sea, and I did this in collaboration with an organization known as TNO, and this is the Netherlands Organization for Applied Scientific Research. And the main reasoning for this thesis is that offshore wind installation is becoming more and more of a high-demand research topic, considering the number of offshore wind farms coming in the North Sea and all around the world. So in essence, my thesis is about modeling this installation process, and what I have done is I have defined the installation of offshore wind submarine power cables using a logistics-based model, which I will go into deeply. Without further ado, I'll go on to the presentation, and once again, thanks a lot for Open Source Study for inviting me. So firstly, I would like to start the presentation by providing an outline of the topics I'll be covering. Some topics I will go into more extensively, and others I will go into in a less extensive manner, just for the sake of time. So most importantly, I'll go through an introduction. I'll give you an idea of the background, the motivation, the research objectives, and then I will give you a very basic idea of what are the aspects that govern power cable installation for offshore wind farms. And then afterwards, I'll go briefly into the installation model. So how do you use an installation model? What is an installation model? And what are the base assumptions that are used? And of course, how does the model accurately represent these processes? And finally, and I think this is maybe the most interesting part, is how you can use such kind of models to investigate the installation of real-life offshore wind farms, such as the Gemini offshore wind farms. And after this, I'll provide a very brief set of conclusions and recommendations. So this is typically how the master thesis outline is. Here, for example, is the first slide, and that's the background. So just to give you an idea of why this master thesis was selected. So typically so now we know that there are lots of new offshore wind farms coming, and the world is experiencing an energy transition. So we need more offshore wind farms constructed around the sea to provide a high level of clean energy. But there is a problem, and you can see this with these quotes. So cables are a very important part of offshore wind farms, and they are used to connect the offshore wind farm to a substation on the land. And it is through these cables that the power from the offshore wind farms are captured and transported. Now the thing is that many of these cables are experiencing failures, and it's a very big problem. As you can see that 80% of the cost for offshore wind farm claims from insurances are coming from cable failures, and cable claims are only 40% in number. And this is a big deal because offshore wind farms are very expensive. So cable installation is going to be the main focus of this master thesis, or the main background. So cable installation is only 7% of the project cost, but it costs 80% of the problem. And why is this happening? And why during the installation phase? So that's what we will use for the basis of this model. So failures originate due to outdated standards and information gaps. So currently, the current standards that are in the offshore wind industry for cables is outdated. They are based on standards set in 2008. And of course, if we want to make offshore wind farms bigger and more reliable, then we need to update these standards. So in order to do this, a big project was arranged, And in this case, it's called JIP-COM, so Joint Industry Project Cable Lifetime Monitoring. It's basically a collaboration between different companies who are trying to investigate how these failures are occurring, and particularly installation. So this is how I got the master thesis as part of TNO. So I worked as part of the team which studies and analyzes installation. So the motivation for this thesis. So the scope of the thesis, so where my work lies, is part of this JIP-COM project. So the aim for me is to devise improvements for installation practices. And how do I do that? By creating a model for how power cable installation takes place. And how I did this is I used a proprietary tool named ECN Install. This is basically an offshore wind farm installation tool. And what it does is it basically simulates the installation of an offshore wind farm. And by doing so, you can understand the different scenarios when you're installing an offshore wind farm. You can take a look at the costs, the benefits, the time taken, and of course you can study the different processes. So as with any master thesis project, there was a main research question which I needed to follow, because of course I cannot answer everything for cable installation. So my focus was mainly how can the processes and strategies used for the installation of offshore wind farm power cables be modeled and analyzed using a logistics model. So under this main research question, I investigated a number of things, and these are the following sub-questions. So first thing is, I would like to understand what the stages, the variables and constraints are involved with installation. So what does it take to perform a cable installation? After that, how can these installation processes be captured and modeled using a logistics framework? So now that we understand what assets are involved in the installation of an offshore wind farm, how can we model this for the purpose of research and analysis? So after this, we want to take into account the factors that impact installation. How can they be incorporated into a model? So if a model is constructed, of course it has to be made more reliable. And finally, after constructing this model, how can we use this to apply for a real case study? So the approach for the research is as follows. So first and foremost is the process capture. So understanding how installation takes place, what are the process logics, and of course, when we understand this, we will know what the requirements are for the model. After this, we will build the model. So how do you implement the processes in the model, and what base assumptions are required? And of course, there are uncertainties that require identification. So what are those input uncertainties? And finally, a case study. So once the model is ready, you can check how we can apply this model to a real life scenario. Is the model useful? Is the model giving good results or not? What are the aspects of this project? So first and foremost, we would like to understand what are the stages involved in power cable installation. Typically, when you're laying the power cable for an offshore wind farm, first thing that happens is a feasibility analysis. So the team gathers information and secures permits for the permission to work in those land areas. So usually these are from the government. After this, what happens is a desktop study. So a team of engineers will scope the terrain, and they will perform a marine survey, and they will perform a risk analysis to identify whether the land which the cable has to go through is good, if there are rocks, how does the terrain look like, and of course this gives an idea of how dangerous the operation is and how much it might cost. So after this, typically what happens is route engineering. So a couple of marine engineering activities take place to make sure that the route is stable and that the route is planned in a very optimal fashion for the cable. Sometimes you don't get the chance to follow the best route. Sometimes you have to take a less optimal route, and that could be for safety reasons, and that could also be for the purpose of minimizing any form of damage for the cables. And then, of course, once the route has been determined, and once the marine engineering activities have been determined, and the risks are studied, then a marine installation program is designed. So what this basically means is what is going to be the schedule of activities for undertaking this process. So a marine installation program is very important. Why? Because it is the finalized installation schedule, and all the installation assets are assigned for each cable section. So what are these assets? These are vessels, ships, equipment, men, resources. And of course, this is going to be the stage that is most relevant for a logistics model that we use for this thesis. MIP decisions are very much driven by the route engineering calculations. So the route engineering calculations will be stating that, okay, the cable has to be buried, for example, 250 meters below the sea. So what kind of equipment do you need? That will impact the way the marine installation program is. Now comes the idea of understanding what are the processes in power cable installation. Typically what happens is the cable is loaded on a vessel with a very specifically structured drum, as you can see in this picture. Then what happens is the vessels go to the land side. So usually the onshore substation is somewhere nearby and the cable gets connected to the land. And then what happens is once the landfall is performed, the cable is laid. So it basically rested on the seafloor and it's taken. Once the cable is laid, some activities are performed to protect the cable, and this is most of the time burial of the cable. So once you lay the cable, then another machine follows up and it pushes the cable into the dirt to a certain distance below the ground. Sometimes you might have multiple cable sections that require to be laid and also to be protected. And under those circumstances, what happens is you join these two sections. So cable jointing occurs, as you can see in this image. And once you reach the wind turbine, you need to pull the cable into the platform. So cable pulling is another activity. What are the main assets or the equipment that you need? So cable layer and protection equipment, those are very basic assets that you require. So the cable layer looks something like this. So you essentially have a vessel and you have the drum to carry the cable and you have a certain number of crew. And cable protection equipment is more versatile, so you need it for different purposes. Sometimes you need a plow, which simultaneously lays and buries the cable. Otherwise, you need, for example, a ROV sledge, which buries the cable after it has been laid. And otherwise, sometimes you will need a dredge, which digs a deeper distance so that the cable can be laid. So, installation methods and their decision logic. That's the next point. So now that we know what assets are required and what cable installation typically consists of, there are some installation methods that we need to understand. And these are post-lay burial. So as the name says, so sometimes you need to lay the cable first and then you need to bury it. Other times you can simultaneously lay and bury the cable at the same time. So that's SLV. And finally, sometimes you will be in the situation where you have to create a big trench first and then lay the cable on top of that. And these are determined by many factors such as you can see, water depth. So if the water depth is very high, then sometimes you might need to use a different method. So the sequences are, like, for example, here roughly stated. So if the water depth is, for example, less than 500 meters, the burial depth is the next check. So if the burial depth is between, let's say, 1 to 10 meters, then you would require a simultaneously burial approach. Otherwise, you will require maybe a more sophisticated equipment. So if you need, for example, to bury the cable at greater than 10 meters under the seafloor, then you need to trench first before burying. So water and burial depth determine the equipment that required. And the equipment combination determines the installation method. So this has been the basic logic for the model. So before we get to the model, first thing we need to understand is ECN install and UWISE ML. So what is ECN install? ECN install is basically an industry popular tool used in the offshore wind industry, and it's used to plan and simulate the installation of projects. And how it does this is that it uses a discrete event simulation framework. So what's a discrete event simulation flow? So it's basically a continuous process is broken down into steps that take place in discrete time steps. So let's say, for example, you are walking from point A to point B. In a continuous model, what you would do is you would calculate, for example, the distance between those 2 points, and then you know the velocity at which you're walking, and you will calculate the total time required. And you will know the variation of the progress that you're making through every time step. So in a discrete event simulation flow, what you do is you divide your entire process into points. So instead of saying at 1.1 second I was 1 meter away from point A, you would say that at a time step of 1 second I was X distance away, and then the next calculation would be at point X plus 1, so a very discrete time step, and then the according distance or according state variable will be expressed. So UWISE ML is nothing but the language that is used to describe these actions. So it consists of connecting the entities involved in a process to variables that are defined. So here you can see that. So these are entities. So the vessels and the port location and the distance. And here you can see the inputs. And here you can see UWISE ML actions. So this is basically a typical set of UWISE ML actions that were assigned to the cable installation activities. So cable loading was represented by a work block. Cable laying was represented, for example, using cable transit block. And the inputs are as following. So I don't have to go very deep and in depth into this section. It is merely to give an idea of how these blocks were used to represent different functions. So these inputs are of course planned uniquely per scenario, and that's the key of identifying the usefulness of the model. So how do we select these inputs? That's the next question. And of course, another very important thing, and this is a very basic concept for working offshore, is that you have weather windows. So typically offshore what happens is that you cannot undertake a work process randomly. So you need to be able to see a weather forecast first. And if you know, for example, between 3 o'clock in the afternoon and 8 o'clock in the night, that the weather is suitable, then you would want to execute your actions during that time. So weather windows are a very important factor for work, and that's also part of this model. Typically a weather window time consists of a defined time, so time required to take that activity into place, plus contingency, so uncertainty factors. So for example, like taking into account errors that could happen. So installation methods and base assumptions. Of course, the model is going to describe installation to a very basic level, and therefore the methods need to have some base assumptions. So the base assumptions are this. So typically our installation process is going to start with landfall. This is how it's going to follow the installation activities all the way until an offshore substation. So here's an example. Let's say we are doing a post-lay burial method. So what happens first is cable loading takes place, right? So you load the cable into the vessel, and then after that your cable layer moves and lays the cable, and then what happens is it performs a landfall, and once the landfall is complete, it continues laying the cable, and then it moves all the way to the substation, and once the substation is reached, then the process ends. So these are the respective inputs and the respective variables that go into this process. The base assumptions are the supply order of the cables is perfect. So this is something that is very difficult to capture in the model. So if you assume a perfect supply order, then you can assume the rest of the processes are going according to plan. And another assumption is sequential installation task order. So typically when you install cables, it's not necessary that you will do everything one after the other. Some tasks can be done simultaneously. However, the model for now is quite limited, and the assumption will be a sequential installation task order. So one task finishes and then the other task takes place. And the crew are working in 24-hour shifts. This may be the case sometimes for offshore work if things have to be done immediately. And the seabed morphology is consistent. So that's another key assumption, and that is that the seabed properties are not changing. So that means our burial requirements are not suddenly changing. So when applying a logistics model, we have to take into account many factors. So these are, for example, the tension of the seabed and the slack. Slack is a very important dynamic property of cable laying. And these are, for example, how we represent functions of cable installation during a a typical logistics model process. So slack is a very important point that has to be integrated into the model. So slack is nothing but making sure that when you are laying the cable, you maintain an optimal level of tension. So if your slack is too low, then you will end up laying the cable and not following the route properly. But if your slack is too high, you can risk breaking the cable or producing too much tension. So the slack therefore contains the speed of the cable layer. This is simply the formula for slack. And the instantaneous slack calculation is expressed as a immediate change of the cable layer speed versus the route traversal speed. So from this slack formula, what we can do is you can calculate the speed of the vessel. So this is going to be the input for the cable layer in our installation model. So now that this is clear, there are other uncertainties that require to be accounted when installing a cable. So some of these uncertainties have been classified into 3 categories. So process uncertainties, asset constraint uncertainties, and installation strategy uncertainties. So the role of these uncertainties is to set accurate weather windows per installation processes and to identify MIP bottlenecks. So process uncertainties are basically installation task inputs determined using a 4-stage logic flow. So MIP input requirements, the theoretical base is that a cable layer speed is typically between 0.25 to 3 kilonewtons. Knots. Unknowns, so cable property and payout rate relationship. So the model assumption is there is a constant payout rate, so that means the cable layer is providing your cable at a constant rate, and the slack margin is well defined to guarantee a safety. So for the sake of the model to capture the processes accurately, we assume that there is a 10% uncertainty margin over the input value, and this is used for a sensitivity study. Asset constraint uncertainties is very straightforward. So sometimes you would use a different type of cable vessel. So using a different type of cable vessel means it has a different property and a behavior. So that will affect its dynamic properties and therefore its performance. So one such factor that was accounted for the model is the response amplitude operator factor. So this is typically for a cable laying vessel. So when you do this, when you take into account installation task sensitivity, so you identify that the MIP is most sensitive. So the MIP is what? The marine installation program. The marine installation program is most sensitive to cable loading and jointing. So cable loading takes a significant amount of time. So a small change in cable loading can produce a drastic impact on the time required to complete the task. Cable laying does not take much of an impact, and cable jointing does as well, because jointing is very dangerous work that is done offshore. So asset constraint sensitivity. So what if you change your vessel, and what if you change the significant wave height that impacts the vessel during a certain time? So how does that impact your MIP? Well, the results indicate that this affects the MIP very inconsistently. So it's very randomized, as you can see from the graph. And finally, installation strategy sensitivity. So what if you have the same route and you choose 3 different methods for installing? Well, you can see here that burying the cable and laying it simultaneously decreases your work time the most. And if you do a more protective installation method, such as, for example, burying the cable first and then, creating the trench first and then burying the cable later, that will consume the highest amount of time. But these are all the model methodologies that have been taken into assumption. But how well does this model hold? So in order to investigate this, it has to be implemented to a real-life case study. So this right here is a real wind farm. So it's called the Gemini offshore wind farm. It consists of the following wind turbines here, as you can see. And this was the cable layout. As you can see, the cable connects these 2 collections of turbines, and then it goes in between here. You have a joint and another joint here, and you have a substation, and the cable slowly leads to an onshore substation located here. So this was an MIP that was planned for between March 2015 and January 2016. And you had a number of tasks that are performed here, as you can see in the figure. And these were the results of the model. So the key inputs that were given for this process was that the cable loading was planned at 3 to 4 meters per minute, based on the dimensions and the properties of the cable. The cable laying rate was from 0.5 to 1 knots. The vessel amplitude factor was assumed to be 0.6. And as you can see here, the process was highly sensitive to cable loading, and there was a minimal impact on changing the vessel. And the cable sections impact MIP based on the length of the installation method. So once this MIP model was applied, we could compare it to the actual outcome. So the method statement, or what was originally planned for undertaking the cable installation, contained the following installation time for the following cable sections. And the process was supposed to last from March all the way until December. So there were lots of contingency factors planned in between here. When it was implemented in real life, the installation time took a total of 6,480 hours, and it took place from March all the way until November. But on the model, however, the MIP model simulation showed a result where the work took place from March all the way until August. And as you can see, this is very far off. This is very far away from the actual results. And the reasons are because of many numerous uncertainties that were not taken into account in the thesis model. So what are the conclusions of this master thesis? So modeling a power cable installation using logistics tool, MIP stage is the most relevant. So we've seen that the power cable installation consists of root engineering and MIP. It's not important to go very deep into root engineering, but the MIP stage is the most relevant. Dynamic analysis principles such as slack and RAO are good for accurate modeling, but they can be improved further to make the model more accurate. And the MIP is most sensitive to cable loading. Cable loading takes the most amount of time. And case study validation could not be established, so the results were not matching the case. However, this needs to be improved further for future studies. So that is an area of research. So just as I mentioned before, so the scope of understanding MIP optimization remains to be explored. So this is something that requires a lot of research ahead. And integration of additional dynamic modeling principles, such as the effective seabed mobility and burial rates, can actually improve the model's ability to capture these processes more effectively. And finally, future simulations with different installation strategies, uncertainties such as supply changes, installation errors, they require investigations. Thank you very much, and I hope you have enjoyed this presentation. And I would like to mention that in a master thesis, what matters is that you really examine the problem. And for example, in this case, I have not validated the model. Model results have come out far, but that is nonetheless an outcome of research. And it actually paves way for an improvement for additional work. That is always welcome. And thanks a lot. I would really like to thank Abhishek and Open Source Learning for the opportunity to present my thesis. I hope that it has been beneficial, and I would really love to express my availability for any questions about, for example, the thesis or the course or what the program is like. And my thesis is also freely available online on the TheDelft repository. Thanks, and have a nice day.